Our first story tonight comes from the Keck Observatory, one of my favorite observatories on Mauna Kea, and a great place to observe from. Well, some astronomers were observing white dwarfs, and they discovered one that was a little unusual. Well, first of all, a white dwarf is a kind of star, and they're actually on our beautiful red giant diagram here, our HR diagram. Hertzsprung Russell, the two astronomers that put this together. It is a color luminosity diagram where color goes from left to right. As you can see, blue is on the left, red is on the right, and brightness goes from the bottom to the top. It turns out that this is also a sequence in temperature, and there are white dwarfs on this plot, believe it or not. There they are. So they're faint. They're near the bottom of the plot, but they're also kind of, well, white. They're kind of in the middle part of the diagram there where stars are white. And I'll blow them up there. And indeed, they're small too. We've coded these stars to be the right size of what the stars should be. So our own sun is on there. Let me show you where our sun is. Our sun is up in, oh, let me get the pointer. I thought I had it, but I didn't. Our sun is right over here. Our sun isn't red, of course. It's kind of a whitish yellow. But these white dwarfs are about 1/10 the size of our sun, or even smaller, Earth-sized, down to Earth-sized. Sorry, 1/10 is Jupiter. 1/100th the size of our sun is the proper size of a white dwarf. They're not Jupiter-sized. They are Earth-sized. Now, how do they get there to start? Well, stars go through different life phases. So we're going to spend the next 45 minutes going through all the details of stellar evolution. No, that'll come some other time in the future. Tonight we're doing All Space Considered. So we'll quickly focus on sort of a star like our sun, something about that massive. Starts as a cloud of gas and dust, ignites with nuclear fusion down on the center, glows for a very long time. We're talking about 10 billion years or so, expands and cools into a red dwarf. The outer layers at least get cooler. Finally, it goes through a couple other complicated phases, a horizontal branch phase, an asymptotic giant branch phase, but eventually it puffs off its outer layers, making a beautiful planetary nebula, and that little white dot that's left behind in the middle is the core of the star that cools off into the white dwarf. So these are stars that have died. It's the leftover remnants of what was a star like the sun. Now, they are, like I said, about the size of the Earth. Now, these folks that were studying it, as you can see the names here, lots of them on the paper. Chiazzo and Burge were the two main authors on this. Jeremy Heil I was in graduate school with, which I thought was pretty cool. Great guy, by the way, super cool. So Jeremy, if you're out there, hello. Anyway, they found a highly magnetized and rapidly rotating white dwarf that was as small as the moon. So as small as the moon, you might initially think, gosh, if it's not as big as the Earth, it must be a really, really low mass white dwarf. There must not be much stuff there. Actually, it's the other way around. The more mass you pour into a white dwarf, the more it collapses itself, the more it squeezes itself. So they become denser and denser and denser. Now, there is a stopping point, 1.41 solar masses, the Chandrasekhar limit. An astronomer named Chandrasekhar calculated this, and sure enough, we don't find any white dwarfs more massive than about 1.4 times the mass of the sun. This one is really massive. It is about 1.37, 1.38 solar masses, getting right up there to the edge. It's rotating about every 7 minutes, just under that. It has a very strong magnetic field, and its stellar radius is only 1,300 miles. So this is a super unusual object. By the way, is that a strong magnetic field? Yes. Yes. By the way, an MRI scanning machine only has about 7 times 10 to the 4 Gauss. So that's 70,000 Gausses. I mean, so we're talking about anyway, super, super strong magnetic fields. You get crazy strong. Now, what interests me about this white dwarf, not just that it's rapidly spinning, not that it's super massive, but it might explode on its own. I know you can think, well, how could something just explode? Does it just sit there, get tired of being there, and blow up? Well, no. Previously, we knew there were a couple of ways white dwarfs could blow up. You could have two spiraling around one another, and finally they merge. Too much mass there, boom, it explodes. Or you can have a neighboring star. This was actually the first idea we had, that grows, evolves, turns into a red giant, and as it does so, dumps material onto the other star. It sort of goes past the tipping point, it flows over onto it. Add too much mass, boom, you explode as a supernova, a type 1a. Well, this white dwarf might do it just on its own. I know that sounds crazy, but Currently, there are, if this is a young white dwarf, and the fact it's spinning fast and has a strong magnetic field is a sign that it's probably young. They tend to slow down over time. The magnetic field does what's called magnetic braking. It'll slow that white dwarf down. It won't be spinning so fast, so it's probably pretty young. If it's young, there's probably a bunch of stray protons that have yet to merge with electrons and crystallize into neutrons. If there are enough of them there, a neutron weighs more than a proton and electron on their own. If you add the two together, you have more mass than you started with. I know it sounds crazy, but this is how the universe works. So it could grow in mass as it crystallizes. And if it grows past that 1.4 solar masses, it'll explode. Now, will we see anything? I don't know. That's why there's a big question mark there. And it probably won't happen in our lifetime. I'm sorry to say, this is something that may happen in millions of years. It's going to be a slow process. But I don't know if you'd even see anything because there's not a lot of material to interact with. It just goes from white dwarf suddenly down to a neutron star. You don't have a neighboring star. You don't have any material that was flung off as the two merged together. I don't know. I didn't have time to find any simulations on it, but it certainly would cause a lot of energy locally there, and it would be very, very interesting.